So here, for the heel impact, we had stresses in the bottom of the container. We end up with fractures in the bottom of the container. For vertical load, this one failed at the shoulder contact. Those fractures are curving. There's a straight segment. That is a shoulder contact type of a failure. The fractures are concentrated within that area. Thermal shock, we have very few fractures, and they're looping and very graceful as they go around the container. And internal pressure, we have a vertical split with branching in the upper and lower sidewalls.
We have to keep in mind that with the second set, there were two variables involved. The samples were initially heated and then received application of the hot end coating. With two variables, we can't say with any certainty what was responsible for the increase in the strength that we saw. So we have to do a third test.
Let's do an exercise. Let's put all of these bottle styles together. Let's choose a few different designs and come up with some concepts. So for concept A, let's take the top of number 2 and the bottom of number 6 and bring those together into a bottle. And for concept B, let's take the top of number 1 and the bottom of number 5 and bring those into a bottle design. Now, if a filler was to come up with a new bottle design and they were to choose between these two options, these could then easily be compared using our Design Study Plus tool.
And let's go down to the atom level, and let's look at what's happening. So if at the tip of that flaw, we could envision and extract and magnify to the point where we see the silicon-oxygen-silicon bond at the tip of that flaw, then we would know what's happening. That particular bond is what gives soda-lime silica glass its strength. That's the key to glass being strong. Unfortunately, it is susceptible to attack, and that attack can come in the form of water, H2O. Need to look for things like perhaps only 1 or 2 molds actually have an issue. Maybe I can show you which of those molds are, what those issues are, and we can work on those specifically to get rid of that problem. It also gives us a great idea of what the general manufacturing quality is at that point. Just some terminology. Sample selection, when we're doing it routine, you'll hear this often in the glass plant. They'll be called set-outs. And if you hear that term, that simply means that every single cavity on that IS machine has a sample associated with it. And we'll test 1 per cavity. That's a full set-out. So we just took all the bottles from 1 run of the machine. The first thing we can look at is silicon oxide, simply sand. The question often becomes, could I make a glass out of just sand? And the answer is yes. However, that particular glass will have extremely high viscosity. It will be difficult to form it into the bottle shape that we're used to. It will have difficulty in workability issues. So it also will require very high temperatures in the furnace, which will make it a more costly product. So for all those reasons, we don't want to just use sand as our only addition.
So let's see how a polarimeter could be used to measure a flint glass item. Here I have the same jar as before. I have marked my area with the highest retardation, so I've done the same type of rotating until I find that brightest retardation. Next though, instead of leaving that tint plate in, you see that pink background, I'm going to slide it out. I'm going to remove it. The colors are going to go away because now I've shifted from those nice second order colors back to my kind of boring white first order color.